whatever I'm saying. So yeah, I feel like that's a good idea. So look. Let's talk about antennas, okay? For a little bit. Then I'm actually gonna go upstairs and leave this whole live. I might go ride my bike. Okay, look. No, let's talk about, okay, yeah. Let's just begin. Let's talk about antennas, okay? We're gonna start from the absolute basics, from the ground up. From positive and negative charges, we'll start from that point. And it'll build up into antennas. Well, whatever I've learned so far, I've only just started learning electrical things. So, okay. We know that there's positive and there's negative, right? This is the axiom that we start from. There's nothing below this. I can't explain to you, why is there positive? Why is there I can't. We just have to accept. Some things in the universe are positive, some things are negative. This is the axiom of, I don't know. Okay? And what we have to accept is, if you have a particle that's positive, we have to accept this. Coming out from every direction, it's a sphere. Every direction of this particle, let's say it's a proton, there will be fields, there will be electricness just coming out of it to infinity, all the way to infinity. Okay? And the way that we actually describe this, if I actually remember, okay, I took this class a long time. I don't remember the actual, okay, but whatever. Everywhere. And the negative, you could just imagine that they're coming inward. Okay? We have to accept this. So negative has all the fields sucking into it. It's like a sink. Like, you turn on the water in a sink and the water just goes down. So that's like a negative charge. And the positive charge is like a source, like the tap itself. There's just electricness just coming out of it, okay? And yeah, that was kind of a weird thing I just did there. But yeah. Okay, and now we know electricity carries charges, right? Electricity carries charges. I mean, electricity is just charges. I mean, wire carries charges, right? So if you have a circuit, okay, pretend this is my wire. Let's say there's positive charge along the wire, right? And let's say it's a cylinder, actually. So we have a cylinder here that's carrying electricity. What did I tell you? There's positive charges in this wire. So that means there's electric field coming out, perturbating to infinity. Okay? So you could say that every wire that you have in your house, it's affecting all the way to space. A little. Maybe if you reach the Planck level, then there won't be anything left. But there is a little, all the way to infinity, and it travels at the speed of light. In a vacuum. But okay, so we know we have electricness. Okay, but there's something more beautiful than what I've just explained to you. Something even way more beautiful. And when I learned this, I was like, beauty. If you have a charge, let's say I have a positive charge, and I take it and I wiggle it. Let me move it. I wiggled it. What would that do? Around it, in a circle around it, will be magnetic field. A circle around of magneticness. That's magnetic field gets generated when you take a charge and you jiggled it. Magnetic field gets generated. Even if it's just moving in one way. Even if it's just moving one way, magnetic. If I were to wave it, magnetic things generated circles. So look, oh my god. So look, we have to remember two things. This is my wire. Okay, electric field comes out. Magnetic field wraps around. Now, this circle, we could break it into small arrows that make a circle around. Okay, we could break it up. And the thing is, each of these small arrows, they're perpendicular. So it makes a 90-degree angle with the electric field. The magnetic field makes a 90-degree angle with the electric field. Okay? So look. I shouldn't have erased that, but okay, look, let me redraw my wire. Now, in this wire, imagine I had a circuit. This is my input, and it just continues. But let's say I have this piece of metal, and my circuit, I'm not going to explain to you how the circuit does it. We'll just accept the fact that the circuit, sometimes it has a wave like this. So the voltage is going up and down, up and down. So sometimes there's more positive in this area, sometimes there's less positive in this area, sometimes there's so much positive. So, it's not uniform. So the electric field is going to be really big here, small here, really big here, proportional to whatever the amount of current in that location at that specific time. So we have a wave of electricness literally on the wire because there's a changing voltage, and the voltage takes time to travel across. And there's also a changing magnetic. So here's the big magnetic where the peak of the wave is, then there'll be a small magnetic where the trough of the wave is. And a big magnetic here. So look, we have this beauty thing. And we have to explain one more thing. But we need to pin this down in our head. If you have a wire, okay, any wire, and electricity going back and forth, you have a circuit that somehow does it. You're creating electric field, and they propagate to infinity. Infinity! It travels at the speed of light. Okay, look. Now, we have to explain one more thing. Why does it travel at the speed of light? Because that truly is light. That's truly what light is. Charges jiggling, and you're creating the electric field and the magnetic field around it. And we have this, there's two laws. I forget the exact, I think it's Faraday's law. But what it says is you can create an electric field. This says you create an electric field. Wait, I should flip the camera. You can create an electric field from the changing magnetic field. Okay, now remember before we had a wave in our wire, and some points there's a big magnetic, and some points there's a small magnetic, and the wave is moving, so a changing magnetic field. Isn't that what's describing when we have a change in the voltage in the wire? Right? We have a change in the voltage in the wire, and some points have more magneticness, some points have less magneticness. So there's a change in magneticness that generates an electric field. The changing magneticness generates an electric field. And there's also something else. We can create a magnetic field by current flowing in a wire, or there's another way, by a changing electric field. Okay? This is change, but remember, there's electric fields and there's magnetic fields. And this point has lots of magneticness. This one has a little bit of magneticness. Right? So look, an electric field could be generated from magnetic. Magnetic could be generated from electric. What does that mean? What does that really mean? Look. I hope this is kind of making sense, and I hope I'm trying to make this as intuitive as possible as to why radio propagates off a wire. Why radio waves propagate off a wire. Look, we have high electricness, and pretend this is just moving. It's changing. So does that not generate an electric field? It's like the electric field is just feeding off it. The magnetic feeds off the electric, and the electric feeds off the magnetic, and it just propagates. It's called a traveling wave. And I hope I'm making this as intuitive as possible, because I don't know how else to really explain that. That's why light just propagates. The changing electric generates the magnetic, and the changing magnetic generates the electric, and it just feeds off of each other, and it just travels. That's what light really is. And okay, now we just talked about the basics of, I really told you the basics of electronics. All electronics should be derived from this. Okay, now we have to talk about antennas, okay? So I told you how you could generate propagating waves off a wire, right? I told you how you could generate propagating waves off a wire. But look. Okay, no. Now, you have to say something. Pretend I had a battery here. Okay, I have a battery, and I have a big plate of metal. Just a sheet of metal. And then I have another sheet of metal with air in between. And then I had it connected in a circuit like this. What would happen if I do this? There would be positive charge building up here, and negative charges building up here. Just the potential is just here, and it builds up charges. And in between, I have electric fields pointing into the negatives. Why? Because remember, these are like sources. Right? There's electricness always coming off of these. But if they're all here and there's negatives here, all of these guys will want to point to the negatives. They want to go into the sink, right? So we have electric fields pointing, like the source pointing into the sink. Okay, look. Right? So this is just, if you have a plate, they point in this direction. Okay? But look. This is what a dipole antenna does. A dipole antenna. Okay, I have my plate, but what if I put a 90-degree bend in the plate, And what if I put a 90-degree bend in the plate? Well, this is just a capacitor up to this point. So the fields are like this. They're pointing it. But these ones, they go like this. This is a dipole antenna. And you know, if the fields are pointing like this in semicircles, they propagate out. They literally propagate out. This is a dipole antenna. And I think that's the best way I could really explain it. And there's more. The length of your dipole antenna, okay, pretend I have a 100 megahertz signal. So I'm feeding 100 megahertz into here. So this is the positive end and the negative end, right? And you could try to imagine this. The electric and the magnetic fields, they're feeding off of each other. There would be a magnetic field also. If you're applying a changing voltage, imagine I applied a sine wave into this structure. And it would just propagate all this energy just out. Does this make sense? I hope this makes sense. But there's more, there's way more. Because the length of this piece of metal needs to be 100 megahertz. What's the wavelength of that? So it'd be 3 milli divided by 300 milli divided by 100 milli, which is 3, right? So this would need to be 3 meters long. Oh, no, I lied. Divided by 2. So this needs to be 1.5 meters long. And this guy needs to be 1.5 meters long to make it it's called a resonant antenna. A resonant antenna. But it doesn't need to be. It creates standing waves better if you have that perfect length with your frequency. And that's really what antennas are about. Resonance, right? You want to create a geometry that creates a standing wave in your metal. So then you can just propagate waves out. But there's more. There's also something called a monopole antenna. I just told you a dipole, right? Because you have a positive end and a negative end. But what if it was a monopole? What if I had one, right? And I don't know much about this because look, anything I'm saying here, take it with a grain of salt because I'm learning. I've just learned this. I don't really know anything really. Like I just read, like you know, I've just this is me learning. Explaining is me learning, honestly. But there's something I don't understand this one. But there's something called a quarter wave antenna. And they're usually used in monopoles where you have a ground plane. Imagine this is all ground. Like this is your ground. And imagine levitating above it. I have like a quarter wave. Okay, I can't explain. Okay, see, I can't explain it. That means I don't understand it, which means I need to go back and read this book more. But all I could say is there's a different design where you have a ground plane, and this is only a wavelength lambda over 4. So it's a quarter wave. But yeah, I don't understand this, so maybe I have to read more about this one. But it just exists, monopole antennas. What else could we talk about? Oh yeah. Well, no, I don't really understand it. Yeah, there's nothing really. Okay, and I need to go take a break. Because truly this is... There's nothing else to talk about. Oh my god, but... Wow, that turned into a whole lesson. But really the main thing is I need to fix this. That's the real thing I want to really fix. And I don't know, man. If you guys have any questions about whatever... I start over, I just came in. I wish I could, bro. I wish I could, but I'm kind of a lazy guy, honestly. Oh wait, I flipped the camera the wrong way. But there has to be more things to talk about. I just don't know enough. Because if I knew more, I'd just be rambling on and on. But that's where I stop. That's where I just don't know. I just need to read more. Okay, look, there's more things that I've known. Something called directional. Oh yeah, let me just say one more thing. But I don't need a whiteboard to explain this. At some point, electronics design isn't about literal components. At some point, it's not about a literal, like a capacitor or a literal inductor as you think of them as, right? It's not like you're using these parts anymore. At some point, when you're using high frequency, like for example, microwave and RF, it's about the literal shape of your wire. The shape of your circuit, of the circuit on the circuit board, the shape of all the connections is the circuit. And I don't know how to explain that, so I'll just pull up a picture from this book so you could get an idea of what I'm saying here. Let me just go. I know it's on the last page. There's a nice little thing I want to show you. Oh, let me just at least put it on here so you guys could see the beautiful pages of this book. But I don't know exactly where it went, actually. Well, this is the appendix, so yeah, we're not here. It's somewhere over here. Like, you know? And I want to get into that. And it's called like waveguide. But I know that the math of it is just absolutely beauty and scary. But I don't know. Holy. And then, oh yeah, I want to talk. Okay, look, let me talk a little bit about the Smith chart. A little bit. Let's see how much I know, because I don't know. We'll see. Okay, no, first. No, actually, let's stop. I want to explain complex numbers, actually, because it's actually kind of beautiful, and complex numbers are very important. Okay, and I'm expecting that you guys at least learn sine and cosine, so at least you're in grade 10. So if you're in grade 10, you could probably follow along or up. Okay, we know that there's a y-axis, x-axis, and we know we could draw a circle. So circles and triangles are the key to physics. Circles and triangles are the key to physics. Why? Okay, look, I drew a circle. And the circle, you just from looking at a circle, you can say, oh yeah, it's the perfect shape. It's a perfect shape. It's one length and you just rotate it and it's just a beautiful shape. Okay, but triangle is also the next beautiful shape. Why? Because it's three sides. It's not something beautiful about triangles. But okay, if I pick any point, I'm going to pick any point on the circle. And let's say I wanted to know the coordinate of this point. What is that? You just draw up. So you have an x and a y. And what sine does is sine of this angle, theta, gives you the x coordinate. Sine, oh wait, I have to flip this around. Because, so if I wanted the x coordinate of this circle, if this is +1, this is -1, this is -1, this is +1, sine of the angle, if you go in your calculator, press sine of the angle, it gives you the x coordinate. Or is it? No, I lied. Cos. Bad mistake. Cos of that, and sine will give you the y. Okay? So, okay, we know this. This is just basic grade 10. You learn this in grade 10. And you can do this for the negatives, the positives, blah, blah, blah. Beautiful, beautiful, beautiful. But when you start learning electronics, and when you start studying electronics, many times you want to add different angles together. And you could go on Google and you could search up the identity to add phases and angles together, and it looks ugly. It's absolutely horrendous. It's absolutely horrible to add angles within your cos and theta. It's doable, but it's just ugly. So there is a different type of mathematics. There's a different way to represent a circle and this triangle and the theta. And it's more beautiful and it's more elegant in adding angles, and that's why it's used in electronics. Because electronics, many times we have thetas that we want to add together. So let me show you this new type of mathematics. It's called complex numbers. There's a guy named Euler, arguably the guy who changed mathematics mostly. Like Newton is there, up there. Euler is up there. Like Euler is like the dude, bro. There's a bunch of things named after him. But let me show you what he created. Okay, first, if you want to learn what he created, we have to ask a question. Let me ask you guys a question. What's 4 times 4? Do you guys know what 4 times 4 is? Well, if I'm doing my calculations correct, 4 times 4, well, let's do this. This is pretty hard. 4, 8, 12, 16. Wow, it's 16. Okay, what if I do -4 times -4? -4 times -4. Positive 16. Wow. Okay, what if I took the square root of 16? What am I going to get? What two numbers multiply to give me 16? 4. What if I did the square root of 4, negative 4 times negative 4 is positive. How do I get a negative? What am I gonna do? Do you know what the Euler did? You know what Euler did? He defined something. He said, let's call the square root of negative 1. Let's just call it, let's just give it a number. Let's make a symbol for the base. Well, let's call it I. The square root of 1 is 1. So look, I is like the cousin of 1 in a different world of negative roots. Negative roots. Do you guys understand what I'm trying to say here? He just called it, he gave it a symbol. He gave the square root of negative 1 a symbol. Now we can use it. Now if I did I to the squared, that's negative 1. Okay, now how does this relate to a circle? How does this relate to angles? How does this relate to electronics? Oh my god. Let me show you something beautiful. Oh yeah, and by the way, the square root of negative 16 is 4 times I. So you take I, multiply it by 4. But look, this is what Euler does. Remember how we called this Y and we called this X? Forget that. Garbage. Garbage. Let's call this regular numbers are real numbers, like we know 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so we have 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, we have our negative reals. Negative 1, negative 2, negative 3, negative 4. But remember, we created a new set of numbers in negative roots. Remember, we created it. We created it. So now we call it the imaginary, the complex. Now this is, remember how I said this is 1, this is 2, this is 3, this is 4, this is 5. Similarly, this is I, this is 2I, 3I, 4I. So now we have the imaginary set and we have the real set. Okay, let me just erase all these ugly lines because we want to draw a circle now in this plane. Okay? We want to draw a circle in this plane. And let's draw a circle here. I'll show you something very beautiful. Now let's pick a coordinate. What if I wanted to know the coordinate of the imaginary and the real? Okay, well, let's draw a triangle. And this is cosine. This is cos. And remember how we said this is sine. But remember, it's in the imaginary set of. So this is I times sine. It's I times sine. Just like how it's I times 1. Look, I. Like, you know, it's like this is the complex version of sine. There's nothing more to it. It's just I times sine. It's like how I is just the root of negative 1 times 1. Right? But let's say my times 1 was just the portion of sine, right? So that's why we have I times sine. I hope, okay, that was not a very good explanation, but I hope that made a little sense to you. Why this is I times sine and this is cosine. This is the imaginary set, this is the real set. Now this is what Euler, I'm not going to prove it to you. You could prove it with Taylor series or something in calculus 2. When you go into university and learn calculus, you can prove this. I'm not that good at math, but this is what he says. There's a number called E. And this is a beautiful number in calculus for many reasons, but something about this is recursive, okay? Just know that the number E, when you do some calculus on it, it spits itself back out. It's itself. There's something beautiful of this number E, 2.718. It's itself. I can't explain that further. But if you do E to the power of I, the imaginary, times an angle, some angle, right? Some angle. What is that equal to? That's equal to cosine, right? Cosine of the angle plus. And why am I doing plus? There's something called linear combination. You could think of this as a vector. This is the cos vector, and the I times sine vector points at that coordinate. So that's why I'm doing plus. It's called linear combination. Maybe if you learn linear algebra, you might actually understand this even more intuitively, but you get to that point if you add I times sine of theta. Now, you could go through mathematics and prove this, truly prove this, through Taylor series of cosine theta and I times sine theta. But I don't know it off the top of my head. But do we know something about exponentials? What's a to the power of b times a to the power of c, right? We know it's just a to the power of b plus c. We can add our angles very easily because thetas are in the exponent. Now we can add our angles very easily. See, I just, okay. Oh, okay, now, I really hope I taught someone something. Whew. But oh yeah, I could just show you the Taylor series on thing. But yo, please comment if you learned something, because that's it. There's nothing more. I just showed you complex numbers and why they're used to add angles. Yes, we've learned something. Yes, I'm happy. Okay, yeah, good. That actually made sense. Okay. Oh, that's a relief, because I was kind of scared. What if I finish explaining that and everyone's like, oh, you're an idiot. What are you talking about? What are you talking about? You stupid. And then I would have just been here. But okay, that's good. Fourier transfer, I haven't taken a class on it yet, but I know, I know a little cool thing. Let me see. I haven't really learned any of this in school yet. Like, okay, look, I'm supposed to be in third year engineering, but, okay, let me just not even talk about it. But I'm supposed to be in third year engineering. But, yeah. I haven't taken a lot of classes. Everything here that I've ever, all of this stuff is learned from Google. But, because it's just enjoyable. Okay, and I'll just say, like, I'm a big procrastinator, okay? But, yo, let me just say something. I don't really, okay, the Fourier transform, I understand it, because you're just solving the integral times e to the I, okay, doing the omega, and just, it's basically, okay, but, okay, let's talk about something called, okay, let's talk about cell phones. And I only know the surface level information of cell phone. Like, I don't really know. But look, let's just talk about frequency and time domain. So you could have a voltage, right? Voltage, and you could have time, and I could have some signal like a sine wave, right? It just means that at some time it'll be at this voltage. At some time it'll be this voltage. Blah blah blah. Okay, we could also have voltage, but usually it's measured in power. Power, voltage. You could switch between them very easily. But okay, but what if I plot it against frequency? Right? This has a frequency, right? A sine wave have. So this is like one. It's like one frequency. There's no wave. It's just one frequency. Okay, so if you plot, and I could actually show it to you on the oscilloscope. There's something called the FFT, fast Fourier transform. It's a beautiful. Oh my God, we should. There's too many things to talk about. Okay, let me just shut up. Okay, but the Fourier, the mathematics of Fourier allow you to transform from this domain, frequency, into time, or from time into frequency. But what if the signal wasn't so beautiful? What if it was? What if it was that? What if it? Then it would be multiple frequencies. I don't know. It could just be. It could be. I don't know. I'm making this up. But if I do a linear combination of this frequency, this frequency, this frequency, this frequency, add them all up, put it through the Fourier transform, it would spit me back the wave that I'm looking for. Or you could take the weird wave that I want, put it through the inverse Fourier, or I don't know which one's which, but it will take from this guy and spit you that out. Now, why do you want that? Audio processing, video processing, things that have to do with frequencies. You can break them down. Look, have you ever used a synthesizer, or I don't know what they're called? You know when you're listening to audio, they're called a spectrum analyzer. It's like you're listening to some song and all the low frequencies are here, like I don't know, 60 hertz, like all the bass, all the is over here, and all the trebles are over here, like 2 kilohertz, right? And then you see some spectrum where it's like, oh yeah, these frequencies are super high and it's changing with their voices, and you know. But the audio is actually the weird waveform, the random of the audio. But the spectrum, you're putting it through a fast Fourier transform and you're getting it in the frequency. Oh my God, these are actually used in video processing too. Because you can look at your light levels as some wave like this. Each pixel contributes some point, and you can bring it into the frequency domain. And there's something called the cosine, discrete cosine transform. And that's how you compress images. but I don't understand that at all. I just watched a YouTube video about it, so I can't even talk about it. But look, this is what Fourier series is, a little bit. But that's besides the point. This is just an intro into what I really want to say, something called orthogonal frequency division multiplexing. We use cell phones, right? And when was the last time you used a cell phone and somehow you received, and you start hearing someone else's phone call, right? Never. Everyone has their own channel, right? So let's see what that looks. Okay, so we have some voice level or some tower, and let's say this is 1 megahertz, 2 megahertz, 3 megahertz, 4. And okay, I'm calling my mom right now, so I'm using this channel. And my brother is calling my dad right now, he's using a different channel. And my sister is calling my cousin right now, and she's using that channel. And they don't interfere in the frequency domain. They could interfere in the space and the time domain, but in the frequency, there's a specific frequency being used for me to talk to my mom, this one, and my sister to talk to my dad, and my cousin to talk to my brother, or whatever. They don't interfere. They're like squares, right? It's like a square. There's no overlap in these rectangles. Now let me tell you something. If you take the Fourier transform, just say this is the Fourier transform of a rectangle, we'll call it rect. There's a function called the rectangular function of some frequency. You put a rectangle at some frequency. Do you know what this gives you? Do you know? Oh wait, let me flip the camera. Do you know what this gives you? Oh my god. Oh wait, no, I flipped it the wrong way. I need to mirror the camera so you could read it. My bad. But do you know what this gives you? If you've taken Calculus 1, you probably got this as a homework problem. And you have to use L'Hopital's rule. Sine of x divided by x. Well, yeah. I know some people in Calculus 1 have definitely seen this. And do you know what this is? It's something called the sinc function. It's called sinc. This guy is the sinc function. I know you guys learned this. Do you know why? Do you know why they teach it to you? It's the most beautiful function used in cellular networks. Why? Okay, if I were to graph this function, let me just graph it. So sinc of I don't know if I did this. Okay, but look, it looks like this. It looks like this. And there's something very beautiful about this function. There's something, I don't understand it really. I haven't really learned anything really. But if you have these, there's something orthogonal. I don't understand it, so that's all I have to say. There's just something beautiful of this type of function. That's all I could really say, and I don't understand anything else. It's because I just need to learn more things. But your cell phones will use sync. Oh yeah. Oh, I want to talk about something actually. Let's talk about how Wi-Fi. Let's talk about how Wi-Fi actually and Bluetooth. Let's talk about how they're modulated, and how data is encoded in Wi-Fi. Let's actually talk about it. And it's very beautiful. It's something called Quadrature Modulation. So, okay, look. This is beautiful. And I hope this really takes away some of your, like, some people might think of Wi-Fi as, oh my god, man. I've seen lots of videos where it's like, how do you make Wi-Fi out of rocks and earth? Right? But if you're here from the start, and we explain Maxwell's equations in the start, this will make much more sense. But I'm not going to go through Maxwell's equations again, but let's talk about it. So we know light is a wave of electric fields. That's what light is. And magnetic fields in the opposite direction. So magnetic fields would be this way, and electric fields would be this way. So, okay, we know that. It's a pattern, perfect pattern. Sine wave, right? There's a pattern. It repeats. So this is the same as whatever happens from it's a pattern. And you could ask yourself, what is information, right? Our ultimate goal is to encode information using light, right? Wi-Fi is light. Red is light. Blue is light. Microwave is light. Radio is light. X-ray, light. Gamma ray, light. All the same thing. It's just a wave of electric and magnetic fields that feed off of each other. And if they feed off of each other, they just continue to move. The electric creates the magnetic creates the electric, and they just feed off of each other and continue to move. And the source is a charge that's just jiggling, right? It's like a ripple in water. When you wave your hand in water, it just ripples. But the ripple, there's two types of ripples, the electric ripple, magnetic ripple, and they feed off of each other and they just continue to ripple. But What is information? Imagine this. Imagine every day you looked out your window and you've seen a guy that holds a turtle. Every single day you look outside and you see a guy with a turtle. But one day you look out your window and he's not there. Right? The pattern is broken. Information is encoded. Why is he not outside your window with a turtle? He might have got hit by a bus. He might have broken his leg that day. He might have been stuck in the toilet farting, and maybe he never came to your window that day. That's information. Ooh, we learn. We have information. Okay, we have a pattern. What if I made a change to this pattern? What if I made it so big and then I made it really small? And it's so big and made it really small. Is this not information? We have a pattern, but I'm changing it a little. What if I did... I don't know. Okay, but this is called AM modulation, where you're just changing the amplitude. The amplitude of your E and the B field is information. This is called AM. You know AM radio? You know AM radio? I know you guys know. It's pretty obsolete now, but you know, it's called amplitude modulation. You're changing the height of the radio wave to encode your info, and you can put audio in here. The height could be your audio. It could be anything. Okay, look. And we could talk. I could talk about how radio waves are detected and transmitted, but I just feel like we should continue into how Wi-Fi really works. So I just told you AM. Then there's frequency, FM, right? Frequency modulation, and we don't really need to go through a whole visual. But what we're changing now, the change in the pattern is the frequency. We're changing the frequency to the frequency. So to encode some audio, I can just bring the frequency closer and then spread it out. And then bring it closer, and you can make circuitry that detects the changes, the phase changes, and the circuitry will find the proportion and convert it into audio. You modulate your info in frequency. Small changes in a pattern encode data. Small changes in a pattern encode data. And I feel like maybe one day someone can relate calculus and do the change in information in time equals the change in information in time. I don't know what it would equal, but this is just fake math that I just said. But but what does Wi-Fi and Bluetooth and TV cable, how do they do it? This is what they do. Okay, imagine I had sine of x, and let's say I had cos of x. Okay, imagine I had two signals, and I take the signal and I add it and I add it. If I take a sine wave and I add it to cos and it spits something, this is called a quadrature. This is called quadrature. And remember, I could do amplitude modulation and I could do frequency modulation, remember. But what if I did amplitude modulation on the sine wave? If I did amplitude on the modulation on the sine wave, my output wave will get amplitude modulation too. If I did amplitude modulation on the cos wave, there's something called phase. Okay, well, look, I didn't talk about phase modulation, PM. There's AM, FM, and PM. There's something called phase modulation. We're changing the phase, and that encodes your information. But what if I did PM, phase modulation here? Sorry. I did AM here, and I did AM here. If I did AM here, it changes the phase of this. But if I did AM here, it changes the... So look, I have two variables. You could go on Desmos right now and add a cos and a sine wave and change the amplitudes of them, and it'll give you something called a quadrature signal. Now look, I have two variables, right? Now look. Amplitude and phase. Amplitude is the length of a line. Phase is the direction. Look, if I could change my amplitude and where I'm pointing, oh my god, I could point to coordinates. Can I not point to coordinates? If I have control of the length of a line and the phase of it, I could point to anywhere, right? I could point anywhere. Now what if this is something called Constellation Diagram? Let me put coordinates 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. And I do the same thing, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. And I do the same thing here. I can change my amplitude, phase. And each point is given binary. I put 0 here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I encode binary. I can point anywhere. I encode binary. Do you get this? This is how Wi-Fi, Bluetooth, TV cable. But let me tell you something absolutely crazy. I've only draw 4 by 4 and then 8. Your Wi-Fi, 1,024 locations and 512. You know what kind of circuitry? What kind of circuitry? And I don't understand any. I just know this is all surface level info. But I just wish one day, I just want to learn this, bro. Like, who designs this stuff? Like, this is why I like to study electronics, because who the hell did this? What kind of old man in his laboratory, 50-year-old man, did this? It's insane, bro. Okay, but I hope we learned something. But I don't understand, like, I don't know how to make you a circuit out of that, but I wish. Bro, there's just too much things, fam. Like, oh my god. Like, bro. And, yo, trust me, this is surface level. I don't know nothing. If I were to open this textbook, I promise you I know nothing in this book. Trust me, this is surface level. I don't know nothing. If I were to open this textbook, I promise you I know nothing in this book. I just read the first couple pages and that's what I've learned. But look at this. This is the mathematics involved in your Wi-Fi. And I don't get it. And this is all I have to really say. I hope today was fun. I had fun explaining that. But I was supposed to take a break, but I went into a full lecture mode. But that was fun. I just released everything that was in my head over the last couple weeks, bro. Oh. I really just released all that. But anyways, okay. We learned a lot. Good. We've learned things. Good. Perfect. And I have this whole live recorded too. And I feel like this is I might put this one on YouTube because I feel like I did a good one on this. Because I like, yo, I enjoyed that. That was fun. That was sick. You just gave me genius. Perfect. Come on, bro. I know you could invent something. Faithfully, you got this. I know. I had a lot of fun. Good. Yo, this is good. This was actually fun. And this is like motivation for me to learn more. Because if I learn more, then we could do this again and again and again and again until we really uncover what's really there. Because I'm trying to learn this too, bro. Like, it's just like Wi-Fi, Bluetooth, what? Who did this? How do you make it out of earth and rocks and sand? What are they doing, bro? What kind of old man did this? Okay, but... Okay. Yeah. I'm just gonna go upstairs. It's kind of cold where I am. There's just so many things, but I feel like I should just... I don't know, man. Oh, it's too dark. No, that was sick, bro. I need to get a drink, honestly. My mouth is really dry. Do you know much about optics? Fiber optic? No, I really don't. But where's my light switch? My mouth is so dry. What time is it? 2? Oh my god, my shift finished. From where I work, electricians get paid $36 an hour. But yo, you know what they've started to do? There's something called opto computers, where okay, we could talk about logic gates. We could talk about logic gates and how computers really work and how computation happens. Should we explain processors? But the last time I really learned about them was a couple months ago, so it might be a little shaky. Let's talk about processors, like CPUs. Because we might as well. I've went this far. We might as well learn about processors. A little bit. No, there's too much to... No. I've done too much, bro. I can't continue like that. Wait, what was it? Well, no, but originally what I was talking about was optocomputers, where, look, in a digital computer, a gate can only perform one operation. An AND gate can only do one AND at a time. An OR gate can only do one OR at a time. XOR can only do. But what if I had optical gates, an optical AND, an optical OR, optical XOR? And what if I feed different frequencies? What if I fed green light, blue light, and red light? Then I can do multiple ANDs using one gate, because the frequencies don't mix. Remember, we're talking about the frequency domain. The frequency domains don't mix, right? The time and the space domain, they can mix, but in the frequency they don't. So we can use an AND gate with multiple different lights and process multiple data using the same hardware. That's what optical computers really are trying to do, I think. That's what I read. Like, when was that? Doesn't matter. But I don't know. I thought he's talking about electronic functions. Well, this way. I'm sorry. But okay, yeah. I guess we'll do this another day, cause I have to go do some deliveries. Honestly, I need money, bro. I had a shift right now, but it's done. But if you have any questions, I'm probably gonna leave just now, because yeah. No, but yo, I need to solve this problem. Also, like, my main goal in life and right now is to fix this. And there's so many. I know the problem, but I can't really solve it, and I kind of feel like the main problem is one of my chips is broken. You go live? Yeah, I go live every night from like 12 a.m. like Toronto, New York, Detroit, wherever that land is in that time. Like, I always go, well, almost every day. But I don't know about when summer school starts and if I like do other things in the summer. But for now, I'm trying to finish this processor. It's like a 16-bit computer. So what I'm actually trying to make right here, this is a 16-bit, okay, it's currently an 8-bit multiplier. It's supposed to be a 16-bit multiplier, but there's a problem, and I'm going to try to figure that out in however long it takes. Okay, so this will multiply 16-bit numbers in 16 clock cycles. So look, if I go tick, imagine your modern processor goes tick, 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 4 billion times in 1 second, maybe 2 billion times in 1 second. And you go tick, 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 state change, state change, state change, does something, does something, does something, tick, tick, tick. This guy in 16 ticks, if I give this guy 16 tick, 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 ticks, it'll multiply two 16-bit numbers. Now, I had an old computer. I don't know if you guys remember it, but it was over here. It's fully ripped apart. This guy, you want to know how inefficient? That would multiply 16-bit numbers. Sometimes it would take hundreds of thousands of ticks. Sometimes, usually in the thousands of ticks, depending on how big the number was. But that guy always 16 tick, tick, tick. Your modern processor does it way faster. Because the reason why it takes 16 ticks is because I'm only checking 1 bit at a time to do an operation. Right? 1 bit at a time, and I have 16 bits, so 16 ticks, right? That's logic. But your modern processor, it checks multiple bits. I think it's called a Radix 8. We could go check the textbook right now. But your modern processor checks 8 bits at a time and does an operation, So you could think about how fast those guys multiply. They multiply fast. And it's called it's called a Booth recording algorithm. Oh my god. And let me just not say it. Okay, let me just say it. There's processors for, we were talking about the Fourier transform. There's specific processors for Fourier transforms. They're specifically designed to convert from the time to the frequency and the frequency to the time. And you'd expect, you need some crazy logic, but really what it takes is a right shifter and an adder. There's something called the Cortex algorithm. Maybe I don't understand. Okay, actually I do get it. Maybe I know it off the top of my head, maybe. There's something called the Cortex algorithm. And it's how your computers calculate angles. Maybe we should talk about it. Maybe if I could pull this off the top of my head, I think, if I remember, because it's a very simple algorithm. It's not crazy, but there's hardware specific for it to run. Okay, let's do it. Okay, there's 3 equations, and it's a recursive formula. So x of, we'll call it I, plus 1. So the next x is equal to, okay, and we'll just say y of is equal to y. Oh, no. It's x of I plus some sigma of your I of is it 1 over 2 to the I? This looks so complicated, right? It's not. I swear it's not. I swear this isn't as complicated as it seems. I promise. Just bear with me. We'll go through it, and it's so simple. And this one is oh my god, this looks so scary, but it's not. And then actually, I don't really remember the form. Okay, let me take back whatever I just said. Let me just take back whatever I said. Maybe I don't know it off the top of my head, so I can't do it. So maybe I'll just make a specific video explaining it. So yeah, I take back whatever I said. I don't even know if this is the correct formula, because I think this is a minus here. So yeah, I just don't know it. I could go in my room, get the paper, but forget that. I think I should just take a break and come back tomorrow. Because yeah. Whoops. I'm sorry for getting your hopes up on that one. But yo, you could just search it up on Google if you want. There's something called a butterfly element. You could search a butterfly element. And it's called a BE, butterfly element. Okay, yeah, there's nothing else to talk about. So I feel like, I'll come back tomorrow. And yeah. That was fun. Okay, bye guys. Goodbye. We will learn more things another day. Thank you guys for watching. See you next time. Alright, goodbye.